Hello everyone. So in this continuation of CTQ series, today we'll see this discussion remain about the CTQ 9, which is the part 2 of this particular CTQ. So we have discussed four circuit in previous question or previous video. In this video, we'll discuss rest two circuits, which are circuit 5 and circuit 6. So there are three things we have to do for all the circuits: gain calculations, swing at the output, and noise analysis. So first we'll see for these circuits how we can calculate the gain, and after that, if possible, uh, yeah, if time permits for this video, we'll see about the noise analysis. Okay, so let's see the gain calculation first. So I'll pick first circuit. I mean, this is circuit number 5. So yeah, so we'll see the gain calculation for circuit number 5. So in general, for any circuit, what we will do, just if there is any block, again I'll say if there is a block, this is the input and this is the output. Then we will do one thing only. First step, this step 1, we will calculate the short circuit transconductance. V is there, so we will calculate ISC here. So short circuit transconductance is nothing but is the ISC by V. And second thing that we will calculate is R out. Okay. In that case, V in is shorted and we will calculate R out. Then overall the gain is nothing but GM short circuit times R out. This is the gain. So this is the fundamental steps that always we should follow to calculate the gain for any particular block. Now look at the first circuit. So what it is happening here, actually this circuit is nothing but simple a current source which is feeding as a load, and Cascode device is used. I think some of you might be known of this Cascode device. This is our Cascode device and it is the input device. Okay, input, we are taking the output here. It is the BP. Okay. So first thing is what? GM calculation. So this is the current. What we'll do for the short circuit transconductor calculation, we'll short this DC points or DC voltages because we want to see the change. What is the transconductor? It's nothing but a change in output current observed for the change in input voltage. So it is an incremental value. So we'll avoid this thing. If this is the ideal current source, then we can open it. And for this Cascode device, we can short the input. And this is your short circuit output current. We call it ISC. Okay. And input incremental or the signal what we have applied will remain applied here. So we can analyze it in a way that what is the ISC. So one thing is that we have the only source which is generating the current is this input device. Okay, it is having input as a V in signal. So here the signal generated is GM, or I say GM if I will call it M1, M2. I will say GM1 V in. Okay, so this is the only current generated by this device, and there is a no other path. So it has to follow this path. So what I can say, this ISC is nothing but minus GM1 V in. So what is this ISC by V in? It is nothing but minus GM1, which is called the transconductance or short circuit transconductance. So we can see here if the Cascode device is there, the short circuit transconductance seen at the output is nothing but a transconductance of input device only, which is a GM1. So now we'll calculate what the other thing, that is the R out calculation. So second thing is R out calculation. For that, again we will open the DC sources with the current. We short the DC voltage source. The same thing is there. So we'll current. So here there is open. Okay. So again we'll short this also because all the inputs are shorted here. Okay, now I'll apply a test source here. Let apply a test source VT, and the current is IT. Okay. So this is the test source we have applied here, VT and IT. Now what is R out? R out is VTY. So for time being, if we are avoiding this lambda equal to 0, let's say, then what will be this? Okay, not lambda. I'm avoiding the body effect here, or even body effect is considered. We'll see the entire discussion here. Okay, this is not applicable here. Okay, so what effective resistance can be seen from here is RDS of 1. RDS of 1. Okay, so other way of writing this structure is like this. I can write this is a RDS of 1, and here we have applied this test source VT IT. So this current is flowing across this. So what you can see is IT can be as, if this I consider as a X, then what will be IT is equal to GM of 2, GM of 2, 0 minus Vx. This is nothing but VGS plus what do you say, or GDS. GDS means IDS of 2. So we can see VDS, which is nothing but VT minus Vx by IDS 2. So it is a overall current flowing across the device 2, which is equal to IT. Okay. So from here, what we can conclude, IT is equal to minus GM2 Vx minus GDS2 Vx plus GDS2 VT. I am writing 1 upon RDS2 as a GDS so that we can simplify it easily. So what we can see, minus GM2 plus GDS2 Vx plus Vt. And one more equation that we can write from here is what is Vx? Vx is nothing but IT times RDS1. Okay, so we can write this thing here. So IT is equal to minus GM2 plus GDS2 IT RDS1 plus VT. After separating, you can find VT by IT is nearly equal to GM2 RDS2 RDS1. So this is the R out. Okay. So for cascode structure, you can directly remember for cascode structure, if this is the ideal source and this is the cascode structure, R out can you find how? In the two ways. This is the R down, this is the R up. So as current source is ideal, so I can consider R up is infinite, and R down we have seen the device which is closer to the output, which is the cascode device. So this is your cascode device, this is your input device. Okay, device closer to the output considered for both GM and RDS term. What the meaning of this? So in the R down expression, you will see if this is a M2, this is a M1, you see GM2 RDS2. So these are at 1, and for the lower device, this is an input device, only RDS 1 is considered. So what we can see previously, what was the input when you what was the output impedance when you were looking down, was the RDS 1 only. So in this structure, when normal common source amplifier was there, this was the output. So what was the output impedance in that case? It is nothing but R down. R up was still infinite because ideal current source. So R down was what? R down was nothing but RDS of 1 only. But after inserting Cascode device on top of this input device, what we have seen, our impedance is amplified with a factor of intrinsic gain of device 2. So this was my previous device 1. On top of that, we have mounted other device which is called the Cascode device, and due to this Cascode device, our R out is amplified. Okay, due to this Cascode device, our R out is amplified. So equal R down is amplified with the factor GM2 RDS2 and times RDS1. So what was the previous R out from here to here? We can see it is amplified with the intrinsic gain of Cascode device. So this is the intrinsic gain of Cascode device. Intrinsic gain of Cascode device M2. Okay, this is the intrinsic gain of Cascode device M2. So now IDS is amplified. So what we can see from here, from the perspective of interview, if you want to improve the gain, then cascoding is a one option. But there are challenges associated with the cascoding. Okay, so to improve the gain, to improve the gain, cascoding is one option because R out is improved. R out is now amplified with this factor, and GM is still same as a GM of 1. So what is the gain? Gain is now increased. This is minus GM1. So GM R out, GM2, sorry, GM2, GM2 RDS2, RDS1. So overall, what you can see, the gain was previously minus GM1 RDS1. It was previous gain. Now it is multiplied with the gain of a Cascode device, intrinsic gain. So it is increased. Let it was the factor of 10, so it is also the factor of 10. So now this gain becomes the factor of 100. Okay, so now it becomes a factor of 100. So gain is increased much. So this is one option. The challenge associated with the cascoding is your headroom problem. Problem associated with cascode. What? Headroom. So what is the headroom issue? You have to understand. Roughly, I can say if there is a one device only, here you're taking the output, this is the current load. So what is happening here? From 0 to VDD, from ground to VDD, this is your VDD, this is your ground. Okay, so for output to swing, this much voltage is required. I mean to say, if this device is operating in saturation for a voltage of suppose 200 millivolt, and this particular current source is biased for this means operating in the saturation like 200 millivolt, and what we can see, these 400 are gone now, and our output can swing what VDD minus 400. So let's say this VDD is 1.8, so your output can maximum go 1.6, and lower side can go minimum of 0.2 volt. Okay, so this much swing is available for your output. Now if there is a stack, now if there is a stack of other device, let there is a stack of other device, and it is also consuming 200 millivolt to keep itself in saturation. Okay, let it, so this is the your input device, this is the cascode. Just I'm telling, if there is a stack of two devices and it is also consuming 200, then what you'll see, your output cannot go below this 200 plus 200 400. So the output cannot go below zero point 0.4. It means your swing is reduced. Swing is reduced. Now your output cannot go beyond this 0.4 value. Otherwise, any of your device will enter into the linear region, triode region. Okay. So again, one question comes, which will okay. So this was the problem when we are cascading the devices, then we cannot go much lesser at the output. So now one more question comes: if we are reducing the output, if output is reduced below the 400 millivolt from the above example, or I can say if output is reduced below the 400 millivolt, or it is reduced such that voltage is not enough, voltage is not enough to keep both M1 and M2 in saturation. So now the point is that which device will go into the triode first. Okay. So now the discussion is somehow changed, but I will not tell this thing in detail. You have to think. If this is my BB, this is the IN. So there is a stack of two devices. This is my output. So what I told you that if there is a two voltages, if it is operating at one overdrive, which is I call 200 millivolt, this is also is in saturation for 200 millivolt. These are the overdrive voltages. They are in saturation. Okay. So what is expected that your output cannot go lesser than this 400 millivolt. Now, if you intentionally want the output lesser than 400 millivolt, then which device will enter into linear first? Which device will enter into triode and why? So we have to see this thing. We have calculated the gain and some extra thing we have discussed here. So now the point come for the second circuit. Okay. So this is my second circuit, and we have to see the gain calculation for it. So what is special here in the second circuit? It is called flip voltage follower. Okay. Again, ideal current source is there, and here is my input, and this device is biased from this node. So it's gain calculation. Again, we will follow the both two steps. One, short circuit transconductance, GM SC. Second, R out. Okay. So let move one by one. So for GM calculation, what we will do? We will open this DC current, and V is applied here. So this is coming back to this point, and this is my shorted out. I call it ISC. Okay. So what we can see here, we can assume a voltage which is called this node X, Vx here. So from here, for the lower device M1, what do you see? What do you see for the lower device? This Vx is applied here. So one current component across this device is what? GM1 Vx. One current component. Is there any component which is including RDS of one? No, because VDS is zero. Your source and drain both are at zero. Okay, so only one current component is there. Now look from this angle. So here we can see the source for the above device is ground because we have shorted it, and input is still there. So one current component flowing through it is what? GM2 VA, because GM VGS. S is your ground, so GM2 VGS. Now there is another component of current which is nothing but VDS by DDS. So I'll write here other component is what? VDS. DS means D is your X and S is ground, so this is Vx. And what is GDS? GDS of 2 means simply 1 by IDS of 2. I want to write in terms of GDS. So what you can see from here, this ISC is what? GM2 Vin plus GDS2 Vx minus GM1 Vx. Okay, so from here I can write here GM2 Vin plus GDS2 minus GM1 Vx. So are we able to find this relation of Vx, ISC by Vin? No, because still the Vx term is there. How to eliminate Vx from here? Is there any relation for this Vx and Vin? So let me think for it. So this is your one GMVGS and okay. So this is your Vx. So what is the relation that we can see from here? 0 ISC 0. So GMVGS, VXOVGS, KCL as this node. Okay. So one KCL we can put at X node. So this equation is coming from the KCL at the output node. So this equation is coming from KCL at output node. Now other equation will come from KCL at X node. KCL at node. What we can see, there is a no current because gate is there. So this is your 0 amp. So what we can see from here, GM2 Vin plus GDS2 Vx, which is a current which is coming down, equal to 0 because it is not going there. So from here we can establish one relation which is Vx equal to minus GM2 by GDS2 Vin. Okay. Now let's put this into the first equation. IS equal to GM2 Vin plus GDS2 minus GM1 into GM2 by GDS2 into Vn. Okay, the space is less, so negative sign is also there. I can write how we can write it, GDS2. We can solve it. Okay, GM2 negative sign is taken inside, so it is GM1 minus GDS2 into GM2 divided by GDS2. Okay, and Vin is completely outside of it. So from here we can write, okay, so if we can open it accordingly, GM2 plus GM1 GM2 by GDS2 minus GM2. So from here, okay, GM2 is cancelled. Okay, into V. So what we are seeing here, GM1 GM2 by GDS2. This is equal to ISC V. So what are the short circuit transconductance we have obtained here? GMSC equal to ISC by V in equal to GM1 GM2 divided by GDS2. Okay, so this is the short circuit transconductance we have obtained. What is GDS2? It is nothing but 1 upon RDS2. Okay, so this is you can see and follow the steps. There's a KVL and KCL. It's a KCL only, no KVL as here. So now we'll calculate the R out. Okay, so this is a short circuit transconductance we calculated. Now we will see how to calculate. Again, open it. This is shorted. This is coming from here. So we'll apply a test source and we'll see what is the best possible analysis. IT. Okay. Now again we'll put two KCLs, one KCL at this node and other KCL at this X node. Okay. Now let's see what possible KCL equations are. So KCL at output node. From the KCL at output node, we can write simply there is one current this side, which is nothing but GM1 Vx. There is a GDS component is also there, plus VDS is what? VT by GDS of 1. Okay, so there are two components there. GDS means 1 upon IDS of device 1, which is M1. So what I can write here, now let's see what the other current. Other current is there. Other current is there. Is there any GM2 VGS? So what is the VGS? VGS and then minus VT. Minus VT. Plus there is GDS component also is there. Vx minus Vt GDS2. So there are two components for both the devices. Okay. So what you can see, current IT is what we can say, yeah, KVL we can write here, IT equal to or IT plus the above component, IT plus this component is equal to this component. So IT is equal to GM1 Vx plus GDS1 BT minus, if we'll subtract that, it will be like a plus GM2 BT and minus means plus GDS2 BT minus GDS2 Vx. Okay, so this is the expression. From here we can separate the terms of Vt and Vx. So what is first, we will separate the Vt terms. So what are the Vt terms? Vt terms are GDS1 plus GDS2 plus GM2. These are the Vt terms. And what are the VDS terms? Sorry, Vx terms. So only two Vx terms are there, plus GM1 minus GDS2 Vx. So it is your IT. Now you remove the Vx from this equation. So for this again, there is a no current, 0. So what you can see, minus GM2 VT minus GDS2 VT plus GDS2 Vx is currently equal to 0. Okay, so from here what you can see, GM2 plus GDS2 VT divided by GDS2 is equal to Vx. Put that Vx there in the equation and we can find the relation of Vt by IT, and that is your out. So it is calculations are a lot of there, a lot of calculations are there, but you can see, you can analyze this thing is faster way. So after that you will see the gain is nothing but GM short circuit transconductance times R. Okay, and for simplification you can do one thing. If you want to avoid, you can avoid the GDS component, then it will be better to easy. So easily we can calculate it, but it is not recommended to avoid the GDS because we are calculating the R out, which is nothing but depending on the GDS mainly. So there is a no point of avoiding it. So do the calculation sincerely, you can get the output. So it's a special circuit called flip voltage follower. Flip voltage follower. You can see the advantage of this circuit also. So the other part, little bit I talked about the output voltage swing. So we will see in some other video, if possible, the noise analysis. The noise analysis is important for these circuits where we should have the idea how to analyze the noise. So I'll take a few of these CTQ9 questions and you can get the idea how to analyze in terms of noise of the circuit. Okay, so this is enough for this video. Thank you.